First, we should thank you for the nice talk before we start the question answer session.
All right.
Many thanks. Okay. Yeah. So Raja's question is done. So let's take Abhishek's question. Abhishek, please start.
Yeah. So hi Prasad. A very interesting talk. So I was wondering that for the case where you only had bubble-driven flows, why was the nonlinear transfer picking at the bubble length scale? I mean, does it have to be the case, or?
So when you only have bubble, that has to be the case, because you see the scale at which energy is getting injected is around the bubble scales. So if I inject energy at some scales, only for scales which are smaller than that scales, the nonlinear in 3D, the nonlinear transfers can be active. On the other hand, we have done it. If you look at 2D, what happens is that the same problem, if you do it in 2D, bubbles rising, you see that from the scales which are comparable to bubble diameter to larger scale, there is an inverse cascade. Okay. But you need to know what is the injection scale, and after that only the nonlinear transfers would become active.
So that gets disturbed when you add stirring, because then you have another.
Because then you have another large scale driving, which is leading to another nonlinear transfer up to the bubble scales also.
Right. And I was trying to follow the argument that you had, that this k to the power -1 that you had mentioned initially.
Yeah.
There were some loose ends in that, which from your scale by scale you could make the entire picture clearer. Could you again repeat that?
So look, what Lance and Batal had argued, if you look at their paper carefully, first thing was that they looked at the energy budget only in the liquid phase.
Right.
Okay. And then they said that the buoyancy transfers the energy, and then they use this term that there's a net production because of buoyancy, right, which balances viscous dissipation.
Yes.
Then they said, okay, what does this net production should be equal to? And then they argued, but look, what's happening is that as the bubbles are rising, they generate wakes, but these wakes are immediately dissipated in the vicinity of the bubble.
Right.
So whatever is the energy transfer has to be local. Now, if I assume that, and if I just think dimensionally, if I say that the energy dissipated in the wakes is epsilon omega, and the transfer is local, then the net production, if I have to balance it with viscous, so dimensionally, if you look at it, that has to go like epsilon omega by k.
Right.
Okay? And then they say that I balance with viscous dissipation. Now, there is no reason to believe, right, that that's what would be happening, because if you see the wakes of the bubble, you could have very well said, well, why you think that the U dot grad U nonlinearity, that is not doing any transfer.
Yeah.
Right? And that's what the question even we had. And their argument to that was that if you look at time scales of all these transfers, they argued, and their arguments were based on average quantities. They argued that the time scale for nonlinear transfer is going to be much larger than the time scale of buoyancy production, which is going to be larger than viscous dissipation. So the dominant scale would be then buoyancy production. Then, slowly the smaller scale would be viscous dissipation. So then they said that nonlinear transfer, therefore, is not so relevant. However, even looking at their measures, we realized that when you increase Galilei number, within our simulations, we couldn't rule it out. Because although the ordering was correct, which they had, instead of putting in greater than symbol, I would be more tempted to put in greater than equal to symbol.
Right.
And indeed, when you look at the scale by scale budget, you find that there is a non-zero nonlinear transfer, although it's a subdominant transfer mechanism. The dominant is surface tension induced transfers, and the subdominant is nonlinear, but it's still present. And it's the sum of these two which then gives you the net production, which goes again by dimensional argument. You would argue that, but we verified it. Now, if you ask me, can you prove, analytically that we still don't have?
Right. So it's quite remarkable that you still get the same scaling even with
exactly
mechanism added.
Yes. So that was the thing that somehow Lance and Batal argued in that way, and their net production didn't have this transfer because of surface tension and nonlinearity together. They would have argued it's just surface tension, but it so turns out that the net, if you also include surface tension, and if you, let's say, make a more general Lance and Batal like argument, you still are fine.
Right. Yeah. Thank you. Thanks, Prasad.
Okay.
Yeah.
Okay. Any other question? Please, you can unmute and ask.
So Raja, parasitic currents, I guess, yeah, I mean, those are much smaller than the velocity scales that we are looking at. So those are not relevant here. They're too small to worry about here.
Okay, so if not, then I will ask a question or one remark. Bata's argument, there is I would say technically there's a flaw.
Yeah.
If buoyancy is the only injection mechanism without nonlinearity, there won't be any cascade, right?
Also, Mahendra, surface tension can also lead to a transfer. So that's what we
surface tension can lead to transfer. It's a local, isn't it? So alpha, okay, sir. How is surface? Isn't it local? Like linear term is a non-linear term in the forcing. Is it correct or non-linear term in forcing?
No, so it's a non-linear term because you see, you are in the physical space. It might look like it's local because it's a Dirac delta. But when you go to the momentum space, you see the Dirac delta would expand if you think of it like that. But you could even look at it in physical space. What's happening is that because you do U dot this term, you see that around the surface tension region, you have transfers taking place. And you see the flux that we are looking at is the sum, right? It's the average flux. Correct?
Actually, look, I can. So if you look at thermal convection, so this is what we did for quite some time. So I want to contrast now. After your talk, I got some ideas.
Yeah.
So so the forcing term is alpha g theta.
Correct. In the convection.
Alpha, basically proportional to temperature.
Yes.
So the supply term is temperature multiplied by U.
Yes.
In Fourier space becomes temperature Tk UK.
Yes.
It is local in K. Unlike MHD where there will be non-local because the B dot grad B term comes.
Correct.
Now, so similarly, if at least the buoyancy part, okay, surface tension I don't understand, I don't know, but buoyancy part will be local forcing.
Yeah, buoyancy is local. So buoyancy injects energy exactly at the bubble diameter scales.
That's right.
Yes.
But I see. So you're saying surface tension is non-local in Fourier space?
No.
Because,
so what I'm pointing out is that, so if you think of it like that, you see, because surface tension, if you write it as sigma k Dirac delta x, right?
Okay.
And if you think of it in physical space, it's local. It's close to wherever the bubbles are. Right?
Okay,
so in the vicinity of the bubbles, you would have it, but at each scale, you would get certain pattern for the transfer.
Okay, I understand. I agree. So it is a non-local energy supply, and that can give you, okay, that is fine. Yeah. But if you look at your plots, now maybe you can show B equal to infinity plot again, the energy transfer plot.
Yes.
So what I kind of see is, F sigma is F sigma and pi. If you compare the two,
yes,
they are comparable. No, I mean, kind of okay. Red is
around the bubble diameter.
Okay, yeah. So red is dominant. I see. Red is still dominant.
Exactly. Red is still dominant. It scales small, right? Because the nonlinear term dies off quickly.
So energy supply rate. In fact, you can do the derivative of this.
Exactly.
Right, a derivative will be energy supply rate in the right side.
So that's what I've done, Mahendra. If you see d by dk of pi k plus f sigma balances.
I understand. I want the derivative of f sigma only, not pi k together.
Oh, okay. Sure, I could have done that. Yeah.
So there's one region. So energy supply, I normally keep it in the right hand side. My convention is so d pi by dk is fk minus dk. And Fk is energy supply by various sources. Huh? So if you look at, there is some part which is negative supply rate. If I take the slope, now you're taking a mod, I think, right now. So
yes.
So I think that will be interesting to see whether there is a negative energy supply rate.
Mahendra, so that's exactly the point. If I don't take the mod, the surface tension term, F sigma contribution, is actually negative. So at these scales, the surface tension term is actually injecting energy back into the fluid.
Yes. So I take the F sigma to the right hand side. Do I get all positive, like what you have red curve, or is some part is negative, which you take mod, it went up?
No. So all terms are always with same sign.
Okay. So if I take the derivative of this, I'm sorry, I'm boring other people, but this is...
No, not at all.
So this part, some part where derivative will become in the right hand side. Well, derivative of red is positive in till 1, then it becomes negative.
Yeah. So what happens is, for scales which are smaller than the bubble diameter, larger than the bubble diameter, the surface tension term absorbs energy from buoyancy. So you can say that, at those scales, the bubbles are expanding and, that's absorbing. And then for scales, because you see, imagine this, you have a bubble which is rising, it expands and stretches. Now it's relaxing. So it relaxes via capillary wave oscillations, which are small scales, and you would have lots of waves produced. So those are being now pumped to, those are creating eddies, which are transferring energy to smaller scales. So that's how I think about it.
So F sigma has both the, if they take the derivative, which is the supply rate, in fact, that has both the signs.
Exactly.
So beyond the bigger size, it is taking energy, and
smaller
below
size,
the DT size, it is giving energy.
Exactly.
I think you could highlight it. That is important point, I think.
Yeah, exactly.
And one more, if you compare with convection, in fact, I was mistakenly, I was trying to compare as a similar phenomena, but it is not. In thermal convection, the energy supply rate is at all scales.
Yes.
Okay? It is not what some people say, it is like plumes, small plumes. In fact, the energy supply at all scales, and we did similar analysis for thermal convection.
Yes.
Energy supply rate is at the box scale.
Yes.
Dominantly.
Yes.
In fact, it's K minus 5 third Prandtl number 1. Now, your phenomenon is very different. The energy supply is at the bubble scale.
Yeah. So that's, you remember, Mahendra, I mean, I was discussing with you, so exactly the point. And so it's exactly that way. It's very different. Yes.
Yeah, it's different. So that's why -3 is coming. So energy supply is quite. Is there a system where the bubble is very big, like system size kind of bubble? No.
No. So one could do that. The problem is typically that, you see, I mean, the flows, and I mean, if you do a periodic box, then it becomes difficult, right? Because the flow generated, it sees its mirror, and then it's tricky. So you want to have a
experiment-wise, is there a possibility that there could be big bubbles coming out? No.
So at least the experiments. So people have done single bubble experiments, no? But the experiments which Lance and Batal or Loz's group or Roig and all these guys have done, the bubbles are at max Taylor microscale.
Yes. So it is still small compared to box size.
Yes.
If the bubble is very big, then we'll get 5/3 thermal condition like
exactly. So this is actually,
otherwise it is a very different.
Yeah, one of the questions that referees had asked us that, what would happen in this stuff, because the more recent paper which I showed you, where you have steering, it's still under review in JFM. So one of the referees in the first round had asked us that what would happen if you had infinite inertial range in the bubble. So that's a very important question. But then the interaction of turbulence with the flows generated by such large bubbles is a non-trivial thing. I don't know how to quickly answer.
But I think that would be connected to thermal convection, because that will be like a big plume giving energy, and it may become simple in some sense.
Yes.
But I think physically may not be possible at all. I mean, bubbles are not that big. At least I can't see in a terrestrial environment, but okay, anyway, so that is my question. So any other question? I can take another question.
So by any chance, are the surface tension and the non-linear terms, are they coupled or their effects? Especially less than bubble size and more than bubble size, I see a stark difference between the red and blue curves here. So less than bubble size, so less than KD, I see them very close. The two curves are very close. So and then it's the opposite if I go larger than KD.
Yeah. So that's because around the bubble size, it's the energy injection. So that's the scale of injection.
Right.
That's where I would have expected both of them to be most
roughly the same. Yes, and left of that, the same reason could apply.
Yeah, but to the right, you see the nonlinear transfer is not so dominant, but it's the surface tension via most probably the bubble. You would have relaxation of the bubble, and that then generates wakes, which then injects energy into the
right.
fluid.
So that those wakes will have a lot of length scales involved.
Exactly.
That's why this spectrum is flat, the surface tension.
So
I would like to look at the F sigma. Can I look at your papers to find the expression for F sigma?
Yeah, I can even show it to you. Maybe it's here. So F's, okay. So this is, okay, let me maybe share the paper with, so maybe we can come back to this later, but if there are any other questions, then
I think we can close the talk.